Welcome to a video on linear growth working abstractly. Let's get right into it. On the previous video, I talked about these two formulas for both a recursive form and explicit form for linear growth. Let's look at this example. Consider a population that grows according to the recursive rule. It's the one at the top, right? P sub n equals P sub n minus 1 plus 23 with initial population. P naught equals 57. So the way that we read that is that P naught is where we start, right? That's 57. That's our beginning value. And for any next value, we're going to add 23 to it. So part A says find P sub 1, P sub 2, P sub 3. Well, for P sub 1, we're just going to start with the 57 that we already had. We're going to add in 23 more, which gives us 80. For P sub 2, without writing it all out, we're just going to continue to add the 23. So 80 plus 23 is 103. For P sub 3, we're going to add in another 23 to that. It gives us 126. That's part A. For part B, we're going to find it quite a bit more challenging because it asks for P sub 200. Well, I don't want to add 23 a bunch of times. So I'm going to combine this with part C, which says give an explicit description of the population sequence. So when you have a recursive sequence, you can convert it to an explicit form as long as you have the key elements. One is where do you start? P naught, we have that, that's 57. And then D, which is our common difference, how much it's changing each time, is given right here in this formula as well as 23. So in part C, we're going to do that actually first. We're going to do it out of order. The explicit formula would be P naught, 57, that's where we start, plus 23 times the N, which is the amount of time or the term number itself. So going back to part B then, if we want to find P sub 200, we can just plug into the formula that we have here in part C, and that is take 57 plus 23 times 200. I'm going to grab a calculator. 23 times 200 is 4,600. Adding in the 57 is 4,657. Okay. So we don't have a story. It's just working abstractly. Let's take a look at a couple more examples. In this example, consider a population that decays according to a linear model. Decay just means that it's going to shrink rather than grow. Initial population, P naught is 520, and the common difference is D equals negative 20. There you see the common difference going down. That's our decay. So A, find P sub 24. Well, I think it's pretty obvious that the explicit form is going to be much easier. So in part A, we're going to start by writing the explicit formula. P sub n equals P naught, 520, plus dn. Now, I could put plus a negative, but I'm just going to write it as minus 20n. So in A, P sub 24, we're just simply going to take 520 minus 20 times 24. Don't forget your order of operations. I'm going to do 20 times 24 first. This piece is 480. And then 520 minus 480 gives me 40. So P sub 24 equals 40. Part B. Part B asks more an equation question. How many generations will it take for the population to reach 10? So what we're doing with the formula that we have here is we're going to consider what if this left part, this population part, equals 10. So we're going to take that formula, set P sub n equal to 10. So when does the 520 minus 20n, when means what is the value of n? When does that equal 10? So using some linear algebra skills, the first step would be to subtract 520 from both sides of this equation. That's our inverse operation. Leaving this with negative 510 on the left equals negative 20n. Don't forget, we would still have that whole entire term, right? And then we divide both sides by negative 20. Well, 510 divided by, or negative 510 divided by negative 20 would be n equals 25.5. So we're going to need to round this because it says, how many generations will it take for the population to reach 10? Well, that means if we have 25 and a half, that means in the 25th generation, it didn't quite reach it. So, because it took 25 and a half. So we would just say, well, it rounds off to the 26th. Or it would take the next generation to reach as low as 10. And then it says, how many generations will it take for the population to become extinct, meaning there's none left? So that would be in part C, when P sub naught, or P sub n, excuse me, equals 0, when this left side is actually equal to 0. So you would solve this equation right here. Well, if you take the same steps, subtract 520 from both sides, you're really just solving when is negative 520 equal to negative 20n. So 520, we just divide this by this, we get this is exactly 26. So this previous one in part B would happen halfway through the year, 25.5, or rounding off to 26. But actually, at the end of the 26th year, it would be exactly equal to 0. So just a half a year difference only. Let's take a look at another example. All right, this one we have a little bit different information. This one says, consider a population that grows according to a linear growth model. The population of the 5th generation, that's P sub 5, equals 37. And the population in the 7th generation, P sub 7, is 47. Okay, so what we're trying to do is find the common difference. So what we need to think of is that P sub 5 really stands for the 5th term, right after the original generation. That's 37. We don't have information about P sub 6, so I'm going to leave that blank. But we know that P sub 7 is 47. So what you're trying to think about is what would be the common difference to take us to P sub 6 and then on to P sub 7. Now, when it's relatively small like this, you could probably guess. You could probably see after a little bit of work what value you would need to add. And it might be obvious, it might not, but if you add 5, you do 37 plus 5, you should get 42. And if you add another 5 to that, you get 47. So that would mean our common difference is really 5. Right? That's the answer for A. Find the initial population. Well, again, if it's relatively small, you can work your way backwards. Like you can figure out what is P sub 4, what is P sub 3, what is P sub 2, what is P sub 1, and what is P naught, which is actually the question here, right? So the idea would be, well, if we're just adding 5 to get to the right, we could subtract 5 to get to the left. Okay, so let's take a look at that. If we do 37 minus 5, it's 32. That's P sub 4. P sub 3 would be 27 by subtracting 5. P sub 2 would be 22. P sub 1 subtracting 5 would be 17. That would mean P naught would be equal to 12. Okay. And then finally, it says, give an explicit description of the population sequence. An explicit description would be following this format right here. And that would be P sub n equals P naught, we found that to be 12, plus the common difference, 5 times n. But the question remains, what if the numbers were further apart? What if it was not so easy just to write down all of the terms like you saw me do above in this situation right here? Well, let's take a look at one last example that would deal with that. Okay, so what if an arithmetic sequence, or by the way, that's a new term I'm kind of introducing here. It would be a linear sequence as well, arithmetic with some authors, has A sub 42 is 1,246 and A sub 74 is 894. Find the initial population, that's P naught, and the common difference. What is the value of A sub 10? Now, this time you can see it's not so easy to write them all down. Like I don't want to start with A sub 42 and write A sub 43, A sub 44, A sub 45, all the way up to A sub 74. That would take too long. So we just want to think about it rather. Okay, so if A sub 2 is 1,246, how many terms did it take to get to the 894? In other words, how many terms elapsed here? Well, that would just be 74 minus 42. Right? 74 minus 42 is 32. Right? So that'd be 32 terms later. And then how much was the change? And that would just be by looking at the change from 1,246 down to 894. Now, you can see that it went down. Right? It went down. I'm gonna write it as a negative. It went down 352. So the idea is that your D, and I'm going to write it down here below, your common difference can be found by looking at the change in the population value. That's the change in the population, change in P. And you divide that by the number of terms that it took. That would be the change in N. All right. So looking at that, our change in P, it went down 352, right? But it took 32 terms to do that. Well, on your calculator, go ahead and divide that. Negative 352 divided by 32 ends up being negative 11. Now, we could have applied that in the previous one. So let me just go back and show you for a moment so you can make the connection. And you can always pause the video and come back to what I just did. But if that previous video, I didn't do that, but I could have, right? I could have said, okay, if you examine right here, right? If you examine P5 to P sub 7, how much did it change? What was the change in P? Well, it went from 37 to 47, right? So that was a change of 10. And how many terms did it take? Well, it went from the 5th term to the 7th term. So my change in N would be 2. 10 divided by 2 is 5. And again, that was our, remember that 5 was our common difference, right? That's what we found in the previous problem. So we're doing that here on a grander or larger scale, right? We're finding that the terms went down 352 in 32 terms. So our D is negative 11. Okay, that's the first piece we need, right? That is our common difference. So we have that. Okay. Now we need to find the initial population. We need to find P sub naught. That's really the next question. Because with those two pieces, then we can write our explicit form and we can find the value of A sub 10. How are we going to find P sub naught? Well, what you're going to do is you're going to use the equation and plug in what you know. So the equation is P sub n equals P naught plus D times n. Now, we already have found D, so I'm going to plug that in. D is negative 11. Now, the other piece that we want to find is P naught, but we can use one of these terms to figure it out. So let's use the first one. Let's use the fact that A sub 42 equals 1,246. What that means is when I plug in 42 for n, and I'm going to do that right here, right? When I plug in 42 for n, I may not know what P naught is, but what I do know is that the answer, right, A sub 42, or it could be thought of as P sub 42. I know I'm interchanging letters here, but this also could be P, and we do that interchangeably. P sub 42 will be 1,246. That means this will be equal to 1,246. Well, if you do 11 times 42, what you get is 462 equals 1,246. So we're going to solve this with a little algebra, right? We're going to add, the inverse operation would be to add 462 to both sides of this. And so we have 1,246 plus 462 is 1,708. And what we find out is P naught equals 1,708. Great, that's been solved. So now we're ready to write our explicit formula, all right? Explicit formula, P sub n equals P naught, we just found that to be 1,708, plus D times n. And D is negative 11. So instead of writing plus, I'm actually going to write minus 11n. That is our explicit formula. And that's very powerful because we can find any term we want right now. And the question actually asks, if you look back at the question, what is the value of A sub 10? So now it's nothing more than just plugging in. And I know that I'm using P and A interchangeably. So let me write P sub 10. P sub 10, which would just be a matter of plugging in 10. All right. So I need to do 1,708 minus 11 times 10, which is 110, and I get 1,598. So the power of that explicit formula is it takes us anywhere. I hope you learned a little more about just working abstractly with linear growth models.